For as long as aircraft have existed, the materials that make them fly have followed one unbreakable rule. Aluminum, or increasingly, carbon fiber. Never wood in any serious structural role. Never anything organic. Anything grown rather than engineered in a factory, precision cured in an autoclave, or milled from a solid billet of metal. In early 2026, a tilt-rotor drone lifted off from a field in Tianjin, climbed into forward flight, and landed itself, with more than a quarter of its entire airframe built from a material most engineers spent a century dismissing as a hut material. Not decoration. Not an experimental panel bolted on for show, tucked away somewhere structurally unimportant just to generate a headline. The entire outer skin of the fuselage. Bamboo. If a plant just did something aviation engineers assumed only refined metal and woven carbon could ever do, stick around. Because this story goes a lot deeper than one drone, and if these kinds of quiet material science upsets are exactly what you come here for, go ahead and subscribe before we get into how they actually pulled this off. Because the engineering behind it is stranger and more deliberate than it first sounds. To understand why this matters, you first need to understand just how unforgiving aviation material science actually is. A car panel that fails is an inconvenience, something you pull over and deal with. An aircraft component that fails mid-flight is a catastrophe. Which is why the entire industry operates under a standard almost no other manufacturing sector has to meet: airworthiness certification. Every material used in a structural role has to prove, through exhaustive, repeatable testing, that it behaves identically every single time, under every temperature swing, every vibration frequency. Every fatigue cycle it will ever experience across the aircraft's entire service life, whether that life spans a few hundred flight hours or several decades. There is no room for a component that performs beautifully in 9 out of 10 samples and unpredictably in the 10th. Aluminum earned its place in aviation because it offered an extremely favorable strength-to-weight ratio combined with nearly a century of accumulated data proving exactly how it behaves as it ages, corrodes, and fatigues under real-world flight conditions. Data collected across countless commercial and military aircraft flying millions of cumulative hours since the earliest days of metal skinned. Aviation. The very first all-metal aircraft ever built, a German monoplane called the Junkers J1, flew back in 1915, and by the 1930s aluminum had become the undisputed standard, carrying passengers aboard aircraft like the Douglas DC-3, and later powering the entire Allied bomber fleet through the Second World War inside aircraft like the B-17. For roughly 70 years after that, aluminum simply was the aircraft industry. Full stop. Composites entered the picture gradually rather than all at once. Fiberglass first showed up in a commercial jet with the Boeing 707 back in the 1950s, making up barely 2% of the aircraft's structure. A token experiment rather than a real structural commitment. Real carbon fiber composite did not arrive until 1984, when Boeing cautiously replaced the horizontal tail structure on a 737 with a single carbon and epoxy component, treating it as a closely watched study rather than a production decision. It took more than 2 decades after that single tail section before Boeing trusted composites enough to build an entire airliner around them. The Boeing 787 Dreamliner, introduced in the following decade, finally pushed composite material past 50% of the aircraft's structural weight, cutting roughly 1,500 separate sheet metal parts and somewhere between 40 and 50,000 rivets compared to an all-metal design, while carbon fiber itself offers something close to 7 times the strength of aluminum alloy at an equivalent weight. So what does that entire 70-year timeline actually tell you about how aviation treats new materials? It tells you the industry does not casually swap one proven material for another. It took carbon fiber more than 40 years to travel from a single test panel on one tail section to 50% of an entire commercial airliner. And that is precisely the kind of glacial, evidence-demanding pace bamboo composites is now being measured against. For decades, those were considered the only two serious options on the table for anything structurally load-bearing. Anything organic, anything grown rather than industrially engineered from mined ore or petroleum-derived fiber, got dismissed almost immediately. For reasons that were not unreasonable given what engineers actually knew about natural materials at the time, bamboo carried a version of the exact same reputation problem that has followed it into construction and infrastructure elsewhere. A stigma that took decades to earn and has proven just as stubborn to shake off in aviation as it was in architecture. In its raw, untreated form, bamboo is inconsistent. One stalk cut from a grove can be notably stronger than another cut from the very same plant, sometimes from the same clump of shoots growing side by side. It is hollow, which complicates structural joining in ways solid metal or woven fiber simply does not have to deal with. It splits unpredictably under fastening loads and degrades if not properly treated against moisture and insects. None of that sounds like a promising foundation for an aircraft component that has to survive repeated flight cycles without a single unpredictable failure, let alone hold up to certification testing that assumes every sample behaves identically to the last. So, what changed? Not the plant itself in any meaningful biological sense, but what a team of Chinese researchers decided to actually do with it, treating it not as a natural material to be used more or less as it grows, but as a raw input to be broken down and rebuilt into something engineered from scratch. The project came out of a partnership between the International Center for Bamboo and Rattan, Beihang University's Ningbo Innovation Research Institute, and a company called Long Bamboo Technology Group. Beihang is not a minor academic footnote here. It is one of China's premier aerospace universities, with deep roots in military and civil aviation research stretching back decades, which tells you this was never a casual side project cooked up to generate a viral headline. When an institution with that kind of aerospace pedigree attaches its name to a bamboo composite program, it signals the research was subjected to the same rigor that university applies to programs involving fighter jets and satellites, not a watered-down version of it. Qin Daoshun, the project's lead researcher and director of the International Center for Bamboo and Rattan, has been direct about how difficult the underlying engineering actually was. Developing a bamboo-based composite suitable for aviation use required meeting the exact same strict mechanical performance standards every other aviation material has to clear, while also solving separate technical problems around molding processes and long-term environmental resilience that raw bamboo was never going to solve on its own, no matter how carefully it was harvested or dried. According to Qin, the team ran more than 100 separate experiments, each measured against actual airworthiness standards rather than a simplified internal benchmark, before finally arriving at a bamboo-based composite combining high strength, high toughness, and the kind of formability an aircraft skin actually requires to be shaped into aerodynamic curves rather than flat panels alone. So here's the pattern interrupt worth sitting with. What does running over 100 certification-style experiments actually tell you about how seriously this was treated, as opposed to a quick lab demonstration timed for a press release? It tells you the team was not trying to prove bamboo could technically hold a shape under a single controlled test. They were trying to prove it could survive the exact same testing regime that keeps aluminum and carbon fiber trustworthy in the first place, repeated, documented, and measured against standards written for materials that had already earned decades of trust. And that is an entirely different, far higher bar to clear than simply building something that looks impressive once. The aircraft itself is a tilt-rotor fixed-wing drone, capable of vertical takeoff and landing before transitioning into forward flight the way a small conventional aircraft does, combining the hovering flexibility of a helicopter with the range and endurance advantages of a fixed-wing design. It has a wingspan of more than 2.5 meters, weighs approximately 7 kilograms, cruises above 100 kilometers per hour, and can stay airborne for more than an hour per flight. Respectable performance figures for a drone in this size and weight class, regardless of what material built it. More than 25% of its total structure is built from the bamboo-based composite, and critically, the entire outer skin of the fuselage. The part of the aircraft actually exposed to airflow, structural loading, and the elements throughout every single flight is built entirely from this material rather than a small, reinforced panel tucked away somewhere structurally unimportant. According to the International Center for Bamboo and Rattan, this makes it the first fixed-wing unmanned aircraft on Earth to use bamboo at this proportion of its overall structure. Not the first bamboo aircraft component ever tested quietly in a lab setting somewhere. The first one to actually carry that much structural responsibility and fly in front of observers, under real atmospheric conditions, with no controlled indoor environments to fall back on if something went wrong. The flight profile itself is worth understanding in a little more detail, because a tilt-rotor design is not the simplest airframe to test a brand new material on. Unlike a conventional fixed-wing aircraft that only ever experiences one flight regime, or a simple multi-rotor drone that never transitions into forward flight at all, a tilt-rotor has to survive two entirely different sets of aerodynamic and structural stresses within a single flight. During vertical takeoff and landing, the rotors point upward, and the airframe experiences loads much closer to a helicopter. Concentrated stress around the rotor mounts in an airframe fighting its own weight directly against gravity. Once the rotors tilt forward and the aircraft transitions into cruise flight, the load pattern shifts entirely, with the wings now doing the work of generating lift, and the fuselage skin experiencing sustained airflow pressure across its entire surface for the duration of the flight. Choosing this specific airframe configuration to test a brand new composite material on was, in that sense, a genuinely demanding choice rather than an easy one, since it forced the bamboo composite to prove itself across two very different structural environments inside a single test flight rather than just one. Here are the two numbers that make this genuinely interesting rather than just a curiosity piece for sustainability conferences and press releases nobody outside the industry reads. The finished aircraft came in more than 20% lighter than a comparable airframe built from carbon fiber. That claim deserves a pause, because carbon fiber is already about as light as high-performance aviation materials get, engineered over decades specifically to shave every possible gram off an airframe without sacrificing strength. So beating it on weight rather than merely approaching it or matching it is the harder claim to make credible, and the kind of claim that normally invites immediate skepticism from anyone who has spent time in materials engineering. And the raw bamboo composite material costs roughly a quarter of what equivalent carbon fiber cloth costs on the open market, translating into a total structural cost reduction of more than 20% across the finished aircraft once every component and manufacturing step is accounted for. So what does lighter and cheaper at the same time actually mean for an industry that almost never gets to choose both simultaneously? An industry where cost and performance have historically pulled on opposite directions on nearly every major material decision. It means bamboo is not being pitched here as an eco-friendly compromise you accept in exchange for worse performance. The kind of trade-off sustainability-minded engineering often demands. It is being pitched as a straightforward upgrade on two separate axes simultaneously, which is precisely the kind of claim that gets an entire industry to stop and actually check the data rather than dismiss it outright as another well-meaning but impractical green materials pitch. The environmental argument sitting underneath all of this is not incidental either. It is a big part of why this research program exists in the first place rather than being tacked on afterward as marketing. Carbon fiber, for all its performance advantages, is genuinely energy intensive to manufacture, requiring high temperature processing and specialized petroleum-derived chemical precursors. And it is notoriously difficult to recycle or safely dispose of once an aircraft component reaches the end of its usable life, often ending up in landfill rather than being broken back down into anything reusable. A growing problem as the drone industry itself scales into the millions of units produced every year worldwide. Unlike aluminum, which can be melted down and reformed relatively easily at the end of a component's life, cured carbon fiber composite is essentially locked into its final shape and chemical structure, and the handful of recycling processes that do exist are expensive, energy-intensive in their own right, and rarely recover material of the same quality as the original. Bamboo, by contrast, is one of the fastest-growing plants on the planet. Some species capable of growing over a meter in a single day, regenerating from its own root system without needing to be replanted after harvest, and requiring a fraction of the energy input to process into a usable composite material compared to carbon fiber's energy-intensive manufacturing chain, which typically involves temperatures well above what growing and drying a plant fiber requires. As global drone usage keeps expanding rapidly, driven by what Chinese officials have specifically described as the country's growing low-altitude economy, covering everything from agricultural drones spraying crops across vast farmland, to delivery aircraft navigating dense urban corridors, to inspection systems monitoring power lines and pipelines across remote terrain. The raw volume of composite material the industry needs is only going to keep climbing year over year, with some industry forecasts projecting the drone manufacturing sector to grow into a market worth hundreds of billions of dollars globally within the next decade. A material that is simultaneously lighter, cheaper, and dramatically less energy-intensive to produce becomes a genuinely different value proposition at that kind of scale, rather than a niche sustainability talking point confined to a single test flight and a press release nobody outside the aerospace trade press ever reads. None of this means Bamboo is about to replace aluminum on the aircraft you actually fly on commercially anytime soon, and it is worth being completely honest about exactly where the real limits sit right now, rather than letting one impressive test flight carry more weight than the evidence actually supports. This is a drone, not a manned aircraft. And the certification bar for anything carrying human passengers sits in an entirely different category of scrutiny, with decades of accumulated fatigue data, redundancy requirements, and regulatory oversight that a brand new composite material simply has not accumulated yet, regardless of how promising its first test flight looked to observers on the ground that day. One successful maiden flight demonstrates the material can perform under real flight loads exactly once, under one set of weather conditions, on one specific airframe. It does not yet demonstrate how that same composite behaves after 1,000 flight cycles, after years of humidity and temperatures cycling across different climates and seasons, or after the kind of structural fatigue that only reveals itself over a genuinely long service life. The exact multi-year, sometimes multi-decade dataset that currently backs every aluminum and carbon fiber component already flying in commercial service today. The research team's own emphasis on environmental adaptability as an ongoing technical challenge, rather than a fully solved problem. is itself a signal worth taking seriously. That this part of the story is still being actively worked out rather than finished and ready for wider deployment. Humidity resistance in particular has historically been one of bamboo's weaker points as a raw material, since untreated plant fibers naturally absorb moisture from the air in ways engineered metals and synthetic fibers simply do not. And proving a composite version of that same material holds up across years of humid coastal operation or freezing winter storage is a very different, much longer test than a single successful flight on a clear day. There is also a scale question sitting underneath the excitement that is easy to gloss over in a short news segment. A 7-kilogram drone with a 2.5-meter wingspan is a genuinely useful proof of concept, but it operates under dramatically different structural loads than a passenger aircraft carrying tons of fuel, cargo, and people across thousands of flight hours a year, cycling through pressurization changes and far more demanding aerodynamic stress than a small UAV ever encounters. In wildly different climates and operating conditions across an entire commercial fleet's service life. Scaling a new composite material up from a small drone airframe to anything resembling commercial aviation typically takes years of additional testing. And that timeline holds true even for materials with far less novelty attached to them than a plant-based composite attempting to unseat what has essentially been a two-material monopoly in aviation for the better part of a century. An incumbency built on trust accumulated one flight, one inspection, and one regulatory filing at a time. Step back, and this story is not really about one drone completing one flight in a field outside Tianjin on an otherwise unremarkable morning. It is about a research team taking a material the aviation industry had never seriously considered, subjecting it to the exact same brutal certification logic that keeps aluminum and carbon fiber trustworthy across millions of flight hours worldwide, and getting a result good enough that the finished aircraft came out lighter and cheaper at the same time. A combination the industry almost never gets to have on any single material decision. It is worth remembering that carbon fiber itself took decades to go from an interesting laboratory curiosity to a trusted structural material inside commercial airliners, moving through exactly the same sequence of small proof-of-concept demonstrations, gradually expanding scale, and slowly accumulating the fatigue data regulators eventually demanded before they would sign off on it for passenger use. A process that spanned roughly the entire second half of the 20th century before carbon fiber earned a genuine seat at the table alongside aluminum. Bamboo composite is, at best, at the very beginning of that same long road, not anywhere near the end of it. Whether it scales from a 7-kilogram test drone into something carrying real cargo, or eventually real passengers, is a question that will take years of additional flights, fatigue testing, and regulatory scrutiny across multiple countries to actually answer with any confidence. But the fact that this question is even being asked seriously inside a premier aerospace research university, backed by a national bamboo research institute, and an industrial supplier rather than a handful of enthusiasts working alone, and dismissed on sight the way it likely would have been a decade earlier, is itself the genuinely new part of this story worth paying attention to. If a plant that aviation engineers would have laughed out of the room a decade ago just flew as the primary structural skin of a working aircraft, carrying real aerodynamic loads rather than sitting quietly in a test rig. What other materials do you think are sitting in that same dismissed category right now, quietly waiting for someone patient enough to run the 100 experiments nobody else bothered to run? Let me know what you think in the comments.